In this workshop, we'll build an, let me just type this, an agentic e-commerce application that supports visual search and voice chats. For the type of e-commerce application, it will be a furniture app. So I want a scenario where you don't really have to type, to search for an item. You can, if you get on the site and maybe you need a particular type of chair and you want to find out if that website has those chairs, all you do is you grab a screenshot or an image of that chair and then you submit it to the website, and then it brings up similar chairs. If it finds it, if it doesn't find it, and then it lets you know. And then for the voice aspect of it, I want a scenario where I can actually hold my mobile phone and speak into it. Like, can I have furniture for my bedroom between $200 and $1,000? And then it brings up a list of furniture for my bedroom if it finds any. And if it doesn't find any, it should actually let me know. So it's like a two-way conversation, a back and forth conversation where I can actually interrupt the agent, the voice agent, and finally, also, if I can think of other scenarios, if I find an item through voice, I would like to actually place an order on that item and have it generate a Stripe payment link where I can make payment and get my item and get my furniture delivered to me. So it's quite a lot. We'll be doing it the 2026 way, where we will use an agentic IDE, and in this case we'll be using Google Anti-Gravity to make it happen. So let's go ahead and just write everything down. So up the top, a couple of prerequisites for this workshop. Prerequisites for this workshop. Let's just change that. I'll need you to have anti-gravity downloaded and installed. So if I go to my browser and I just search for Google Anti-Gravity, we have that, and you can download it from there. Let's go back to. You need to have the AWS CLI downloaded and installed on your command line interface. I don't know what platform you're running on. I'm currently using a Mac. So if you're using Windows or Linux, you actually know where to get it. AWS CLI download. And you get that. And then the way we'll build this application is we'll build the back end and then the front end. Our back end will be building it using AWS services, and we'll provision our resources using infrastructure as code. So in this case, the infrastructure as code framework we'll be using is the AWS CDK. So I have AWS CDK. So you'll have to download this as well for your CLI and install. And then just a basic understanding of building APIs on AWS. If you don't have that, then you can also check out https://educloud.academy, where we have a ton of workshops on how to build APIs. Let me just go there and show you. Yep, so you can just navigate to courses, and you'll see a lot of courses on how to build different types of APIs. Maybe the prerequisites will add more as we dive through the workshop, because I'm really just trying to think of it on the spot. But for now, you need to have a couple of these. Now let's talk about the AWS services, or the services that we'll need in order to accomplish this project. And after that, we'll build the solutions architecture for the back end. Now let's talk about our applications architecture while keeping cost and performance in mind. So as mentioned earlier, I said it will have a back end and a front end. So for the back end, we'd use AWS services. And for provisioning of AWS services, I'll go with the Cloud Development Kit, AWS CDK. And then let's think about the services. Now, what are the use cases for my application? I want it to support visual search. So when I think about visual search, what comes to my mind is vector databases. And in this case, we'll be using the AWS S3 vector database. Because here's how I see it. Now, all the images on our website will have to be broken down into numerical vector embeddings and then saved into a vector database. And then when the user now brings their image to search, what we'll do is we'll grab that image, we break it down into numerical vector embeddings and then do a similarity search. So if our query now brings back results from our database, our vector data store, then we have a match. If not, we have no match. That's why we need the AWS S3 vector database. Bear in mind that there are other types of databases. We have, or vector databases rather. We have Pinecone, we have Milviews, we have Quadrant, we have OpenSearch serverless. But the reason why I'm going with the S3 vector database is because in terms of price, when it comes to building applications, I'm really brutal with the cost. I like to always use, I think about cost a lot. I want to always use tools that will make me develop my applications and actually put it out there and run it for a while before I start getting hit with a lot of payments. So S3 vector database is 90% cheaper than every other vector database in the cloud. Let me show you. S3 vector. I think this is it. So look at this. Cost optimized AI ready storage with native support for storing and querying vectors at scale, reducing total cost by up to 90%. That's exactly why I'm using this. It's cost optimized. It's actually good. It's really great and it's cost effective. So let's go back to Excalibur. We have AWS S3, and then we have for our API, we'll be using the GraphQL API, and we'll be developing that using AWS AppSync. We'll have ourselves a couple of Lambda functions. We'll use the recently released Lambda durable functions for durable workflows, to build durable workflows. So in this case, let me give you a scenario. We'll use Lambda durable functions to build the visual search aspect of our application. Let me break down the use case for you. So what you're looking at is are the steps taken to actually ingest a user's image and then look for similar images and return it back to the user. So at the start, this is the user on your left-hand side, and they submit an image to your application. What happens behind the scene is that image is broken down into numerical vector embeddings. And then using a query, a similarity search is done on the vector embeddings within the vector store. Now, when similar images are found, they are being returned. But with these similar images or with these similar embeddings, each of these embeddings have metadata, and that metadata has the product user ID within them. We'll explain more about this, or we'll talk more about this as this workshop is being unfolded, as we are going through the workshop. So we'll take out this product user ID and then do a batch get to get the product item from the DynamoDB table. When we get the image and the product item from the DynamoDB table, we'll send an event through event bridge back to the user. So back to the application. It can be a mobile app or it can be a web app. For our use case here, we'll be using a web app, as I'll illustrate later. So when a user submits an image, it goes through this entire process, through these steps as a durable workflow, and then back to the user. I hope I've broken this down enough. I hope I've painted a proper picture of how we use Lambda durable functions, and I hope this use case is actually really valid and it makes some sense to you. So after the AWS Lambda function, let's talk about the AWS step functions service or workflow. Now this is another orchestration service. We'll be using this in this case to, first thing is that our application has a lot of, images. And what we really want to do is break these images down into numerical vector embeddings and save them into a vector store. That entire process is also a workflow which has to be durable. We could as well use the AWS Lambda durable functions for this, but I just wanted to show off, AWS step functions as well because it's my favorite AWS service and it's really good for tasks like this. So it's just a scenario where you can pick and choose what you want to use. I just want to give you those options so that when you come in contact with a scenario, maybe you want to go with Lambda durable functions or with AWS step functions. But bear in mind there's a difference between both of them. AWS step functions supports YAML and JSON, while Lambda durable functions goes with Python and TypeScript. So if you don't want to have that disconnect with your application where now I have to deal with JSON and YAML, well, you can as well build your workflows with Python and TypeScript, whatever you're good at. So it's just me, putting all the cards in front of you and having you choose whatever you want to move along with, pick your hand sort of thing. The next service on the list is the AWS Event Bridge service. It'll help us make our application event driven. So we'll be pushing a lot of events around our application. For instance, a user wants to search for a chair, drops an image and then an event is sent. And then when the search completes, an event is sent alongside the data and the user receives it back in real time. So it makes our application event driven. And then we'll have AWS SQS to decouple our application and make it fault tolerant. If it's fault tolerant, scalable. I like those words: performant, cost effective, fault tolerant, scalable. Just throwing out those buzzwords, just nice words in the air. But I think we'll use them properly and we'll use them within the way they have to be used, perfectly. And you actually see that the application works well. Next thing is we'll also use AWS AppSync JavaScript resolvers. So if you don't know about JavaScript resolvers, they're a successor from VTL functions where you get to write endpoints, GraphQL endpoints without using Lambda functions. Remember that Lambda functions actually are costly. They're costly and they have this thing that they call code starts, but they have really reduced. I don't know, code starts have really dropped because these nice engineers at AWS have worked on the feedback that were given and made Lambda functions really, really good. But there's still code starts and it's still costly. Now, JavaScript resolvers actually help us, carry out certain type of activities, build certain types of endpoints that don't really need a lot of compute power without using Lambda functions. And it's great. I'll show you if you haven't seen it before. And if you want to learn more about it, you can always come to EduCloud Academy. We have, and then what next? I think, is this it? Oh, we have AWS S3 buckets to store our images or the data within our application, blob data, then AWS DynamoDB for records. And if there's something that I should talk about here, is let me illustrate that. All right, let's say these are images. I hope I'm illustrating this the right way. Now, if we just create numerical vector embeddings of each of these images and save them into our vector data store, and now a user searches for, let me say, a t-shirt. All right, we now grab t-shirts from our vector database, but how do we match the t-shirt in the vector database to its record? Remember, each of those items on an e-commerce site, I mean, they have details, they have a record, they have to be saved somewhere. How do we make that correlation between the item, the numerical vector data within the vector data store and the item in a relational database or NoSQL database? In this case, we're using DynamoDB. They have to be a correlation. Now, when saving vector embeddings into a vector store, you have the possibility to add what they call metadata. So what we'll do is that for each of these images, let me say this is an image, or let's say this is an image. This image will have a metadata just off the top. We'd have the image name as found in the S3 bucket, because these images will have to store them in the S3 bucket as well. We have the product ID of this image. It will be a UUID. And then we'll have other stuff like the category that this image belongs to. There's furniture, there are tables, there are beds, and all that. So the category can be kitchen tables. Maybe subcategory as well, and other stuff. Now, within our DynamoDB table, we have an item. So let's say DynamoDB. So there's an item in our DynamoDB table with this same product ID. Let me call this UUID1. That's the product ID for this image. So there's an item in the DynamoDB table with this same product ID, UID, and these details, and then more, because there's a cap, there's a limit to the amount of items you can store within a metadata. It should not go above 2 kilobytes. So we store the rest of the information concerning that item within the DynamoDB table. Now, when a user actually queries for a chair, a table chair, what we'll do is that we'll get the numerical embeddings of that chair, and then we pick out the metadata and we extract this product ID. And now we fetch this product ID from DynamoDB and bring back the entire item. I don't know if you actually get the picture. So this product ID actually creates that correlation between the item or the numerical vector data in the vector database and the product item in DynamoDB. I tried my best to make it to design like Picasso, but I'm not just him. I won't ever be him. So let's go ahead. Looking at all of these services, I really hope these are all. Let me think again. Remember we said this is agentic. Look at that. Agentic. And I should have added something like serverless as well. Serverless, not the absence of servers, but the presence of servers, but you don't get to babysit them. And then you only pay for what you use. And it has generous free tiers. But look at this, agentic. So how do we make our application agentic? We would use AWS Bedrock Agent Core. This is AWS's offering of building agentic applications and pushing them to production. So we'll use this alongside its open source Strands framework. Agent Core has a couple of services. In this case, we'll be using first the runtime, which is serverless, and it actually helps us, push our agent to production, take it from demo to production. We'll have the runtime, we'll have gateway. Now, gateway is another service offered by the Agent Core. It's part of the Agent Core service stack. What gateway simply does is it enables us to connect different types of tools to our application. Remember when I was describing this application, I said we'll be able to create a Stripe payment gateway, and then we'll use voice to query data from our database. That we'll have to use what they call targets, because gateway supports a couple of targets, 4 of them. It supports MCP targets, and in this case, our Stripe will bring it in as an MCP server. It supports Lambda targets. In this case, the tools such as get products from DB, get all products, get order, place an order, which we'll create, would actually connect them to our agentic application through the gateway. It supports we have open is it not open AI, open API. I'm sorry, I'll not take this out. It supports open API endpoints, and then it supports SMITI APIs endpoints. But in this case, we'll be using only MCP servers and the Lambda target. And then we'll definitely go with the identity service for security. Each of these tools that we're bringing in have to, they have to be secure. So, and in this case, for the identity, we'll be using Cognito. What else will we be using? This is it. Let me think. We have runtime, gateway, identity. We have memory. You don't want your agent to actually forget what you just did. You want that whatever conversations you had with it, when you come back a couple of days later, you should be able to continue from where you left off. Remember, agents by default are stateless. So in order to make them stateful, we bring in memory. And it also has browser support where you can spin up, browsers and, place orders on websites. It has, what else? It has the code interpreter where you can run background code, Python code, TypeScript code, and perform some computational stuff. And it's all good. And also, just for a basic understanding, the runtime can run for a maximum of 8 hours within a micro virtual machine. And this is actually supported using Firecracker. If you really want to dive deep into just the basics of AWS Bedrock Agent Core, on EduCloud Academy, I have something really short. It's about 20 minutes long. If you come to the search bar and type introduction to Agent Core, let me see. Yeah, this is it. Introduction to AWS Bedrock Agent Core. I dive deep into what each of these services are. And then within EduCloud as well, we have a lot of examples on how I use each and every one of them. So these guys, alongside some specific models, which we would actually introduce also later, will enable us build the agentic side of our application. Now, the next thing after putting down all of this, the next step I'd like to do is, draw out the solutions architecture for our backend. All right, let's go ahead and draw the solutions architecture for this application. Firstly, I would like to bring in the icons that I'll use. Let's type AWS. I'll hit add to Excalidraw. Now, these nice icons have been added. What I'll do is I'll just be searching for everything. AppSync, just click on that. SQS, Event Bridge, Lambda, step functions. What else? S3. What of S3? Yeah. So our request comes through AppSync. Let me increase this. Now the first, all right, here's how I want to connect this. I'll connect them using use cases. The first thing is the images that I have that I want to actually create vector embeddings of them and save into the vector store. Those images will have to sit in an S3 bucket. And I like that this S3 bucket or this functionality to actually ingest the images, it should be handled through AWS AppSync. So what I'll do here is that I'll just have arrows in this indicating that images were added. But nothing happens when these images are added. Don't get me wrong. I just want to indicate that images were added. Let me take this off from here and move it down. It doesn't invoke anything. We'll just add all the images that we want to have saved into the vector data store. And then now we have a Lambda function. Sorry, so this Lambda function invokes ingestion workflow. So if I can connect this. So this Lambda function invokes this step function's workflow. Now this step function's workflow creates vector embeddings of these images. It picks up the images from the vector. Let me just move this down again. Sorry. I'll just move this down. Okay. AWS S3 vector store. At the same time, it saves the item details into DynamoDB. So let me bring in DynamoDB. I don't want the playful one. I want straight. So it saves the vector embeddings for each image into AWS S3 vector store, and then at the same time it saves the item details for that image into DynamoDB. So there's a correlation. All right, now that we're here, let's talk about AWS Step Functions and what actually happens within it. Like I said, it breaks down each image. So it gets the images from the S3 bucket here, and it saves them. It breaks them down into numerical vector embeddings and saves them into the vector store. Now it has a service within it called maps, but in this case, we'll be using a distributed map. And the reason is that distributed maps are efficient and really perfect for use cases where you have a lot of data in the S3 bucket. So distributed maps, we'll use a distributed map to actually loop through each of these images, efficiently create vector embeddings, and then save them into the vector store. At the same time, we should bear in mind that for creating vector embeddings, we would have to use the AWS Multimodal the AWS Nova 2 multimodal model. I think. Let me search for that so that I have the right name. Oh no. AWS Multimodal model. Yeah. Nova. Yep, this one. Let me scroll to it. Yes, this one. This is what we'll be using. And this actually has a limit, on the amount of items that it can process at a time. So we'll have to bear in mind when we are also actually using distributed maps, because for distributed maps, I think we can process up to 1,000 items at a time. But can the multimodal embeddings actually create embeddings for 1,000 items at a time? Nope, you cannot do that. So while we are actually configuring the distributed maps, we should actually think about the limits or the threshold for the embeddings model. I just wanted to put that out there. So this is our pipeline. Images are just put into S3 and then we hit ingest. Ingest. And the process starts and we monitor it. Now let's look at the scenario where a user searches for an item. Just copy this. Remember, it's still one S3 bucket, but with different folders. So let's call this the S3 ingestion folder. Along the line, we might name it something else, but for now, let's just call it that. And then we'll call this a search folder. Now, when a user adds an item or uploads an item to our application, it gets saved into the S3 search folder. Let's just call it the search folder for now. We might call it something else as we're building our application, but for now, let's call it the search folder. So when a user uploads an item, what we do is that we save that item, that image, into the search folder. And when that image actually hits the search folder, it invokes an event. And this event is picked up by the SQS queue here. This SQS queue pushes, or rather, there's a Lambda function that pulls for items within the SQS queue. But this invokes the Lambda durable workflow, or invokes search workflow. Let's call this search workflow function. And this search workflow function keeps sending events to the event bridge. Let's bring in rule. And this event bridge has a rule with the bus attached. Where's the bus? Too much details. I really don't need that. It connects to this a bus and subscribe. This bus has a rule, and subscribe to this rule is our AppSync endpoint. I'm trying as much as possible not to make this look ugly. So it comes back and it feeds the information here for that real-time feedback. So user uploads image for search. And after the search, our API returns a success or a failure. If it's a success, it returns the images that it has found. If it's a failure, it lets the user know. So this real-time feedback is handled by Event Bridge. So here you might ask yourself why we used an SQS service and why do we not just use a Lambda? Now I'm looking at a scenario where we have thousands of, our application is popular. That's really why we're building it, right? We want to be the next big thing. And we have a lot of users trying to search. And Lambda actually has limits. It can spawn, it can create up to 1,000 Lambda invocations. That is good. But remember that each image has to be taken and broken down into numerical vector embeddings using the Nova 2 multimodal embeddings as the model. And there's a threshold on that as well. I think for my case, for my account is about 50. So even though Lambda can actually span that, our model cannot. Bedrock will actually throttle. Bedrock will throw a lot of errors. And then our Lambda function will throttle. When Bedrock throws a lot of errors, now our Lambda function keeps failing, our application will break down. So we want to actually use SQS to make sure that to reduce the possibility of our Lambda function failing. We would use it to actually say, hey, we can process just 50 images at a time. So you guys coming up will have to wait. And at the same time, when we say wait, we make sure that those messages that we've asked to wait, they don't get lost. Even if they get lost, they would get pushed to what they call a dead letter queue, which we can redrive and process later. So you see here that the SQS endpoint actually the SQS service actually makes sure that our application is fault tolerant, strong, and it can actually handle failures gracefully. It only sends, you see this, that's why the arrow here actually points back to SQS, because at this point, what happens here is that the Lambda function pulls for messages. It pulls for items. Say, okay, I can handle 10 at a time. It doesn't receive 100 at a time. It pulls for it. It pulls for the amount that it can handle. It goes and handles it and then comes back for more. That's the reason why we put SQS here instead of just having a Lambda function here, which we could have still done that. Makes our application, it actually really decouples our application and enables us handle errors gracefully. It's a really horrible diagram, but I just try to, when I'm calm and rested, I can build something a lot better than this. But I hope you get the point. And then now we'd have another one. We'd have the Lambda function that invokes our agent. Let's connect this here. Nope. And it saves embeddings back to the S3. Okay, all right. And we have another Lambda function. I'll just have this Lambda function here, and it invokes the agent core endpoint. And I have another arrow from here to here. All right, I went ahead and drew this because drawing while talking made me really tense. So I'll go ahead and explain it. Like I said, we have the agent core runtime, serverless production ready service to deploy agentic APIs to AWS cloud. And then we have our agent core gateway, which is like that mediator between our tools. It has targets, 4 targets. We have the Lambda target, MCP target, Open API target, and SMITI API targets. And then, the protector, which is the identity. And in this case, we'll be using Cognito. And all these are connected to the runtime. So when you deploy this runtime application, it actually returns a URL, and we use a Lambda function to invoke our agent through that URL. Now here, as you can see, our Lambda target, all these items that are saved into the DynamoDB table, we want to be able to agentically start a word. You want to be able to retrieve them in an agentic manner. So we want to get all products. We want to get product by product ID, add products, or add a product, delete a product, and you can add in so many tools. And there's also something called fine-grained access control offered by Agent Core Gateway, where, take for example, you don't want every user to be able to add a product. These tools should be slated. It should be reserved only for admins. So you can use fine-grained access control to actually let only admins, add products. But in this workshop, we will not be implementing that. That's left on to you to go online and research on how to do that. Do it. Put this project up on your own portfolio and go for job hunting. At the end of the day, that's really what we want. So here, the Lambda target now exposes these tools to our API or our Agent Core Gateway, and Agent Core Gateway now exposes those to the Agent Core runtime, and it can be queried. So from our front end, we can query for all products or for products of a specific category or whatever, and it brings it back. Same, we have the Stripe MCP target, which in this case we will now use to create Stripe payment links. And then agent core memory, because agents by design are stateless, and now we need them stateful. Agent core memory comes with a couple of different services within it. We have short-term memory, and then we have long-term memory, where short-term memory is synchronous, and now it grabs information from the short-term memory and it saves it in a synchronous manner to long-term memory, and that long-term memory in the back end is a RAG. So if you really want to know more about Agent Core, really just come here and search for Introduction to Agent Core, and you'll find it. It's really great. It's very simple, and you definitely enjoy it. So this is just about it. So this Lambda function invokes Agent Core runtime. Put this. Yep, and then our agentic framework is Strands. And that's about it for the solutions architecture of an agentic e-commerce application, a serverless agentic e-commerce application that supports visual search and voice chats. Now let's work on the data for our application. I went ahead and searched for IKEA. I saw a GitHub repository that had an IKEA dataset, and it has zip files of a ton of images. I think there are about 12,600 images. No. And we wouldn't be using 12,600 images. As a matter of fact, I think that you should use a maximum of 20 just to test your application. I went ahead, a while back and used about 6,000 images, and my AWS Step Functions workflow costed, plus the multimodal embeddings model costed about $20 on AWS. And for me, that was great. I was testing, and as an AWS Service Hero, we get credited with we get given AWS credits, to play around services and build workshops and tutorials. But for you, I don't know if you have that much. If you have AWS credits, or maybe you want to spend your own money. But for this use case, I think you should just maybe use 100 maximum, or 20, just to be within that free tier limit. So what we'll do here is that we'll grab these images, we'll grab these zip files and just process them. What do I mean by process them? Remember, we said that we need that each image should have metadata, and that metadata will be saved alongside other data as an item, so that there's a correlation between the image in the vector store and DynamoDB. Okay, let me show you something. So if I click on babychildren.zip, and then I click on this download raw file. So I've downloaded this babychildren.zip, and if I unzip the file, what I have here is the unzip file. If I double click and open it, I see that within that file I have two files, baby and children 3 to 7. If I click on children 3 to 7, I'll see more folders, rather. I'm calling files folders. These are folders, sorry. So I see more folders, and within the children bed folder, I can see children beds. So here's what I want. I want that each of these folders, this should be a category, and then this should be subcategories. So what I want to do at this point is create a script, an agentic script that goes through each of these files, grabs the folder names as category and subcategory, and then dynamically creates product items or product item names, product UUIDs, and a couple of other details as metadata for each of these images. Let me show you what I'm talking about. So I want to build an agentic script to extract relevant information that I need from each of those folders. I want it to extract the category, which is a folder, the subcategory, which is the folder within a folder, and then it should generate a product UUID, universally unique identifier. And then what else? It should generate image name as saved within the S3 bucket. Let's go back to prerequisites and add the fact that we need to have Python on Strands, of Python on Strands CLI. So the first step is to go to Strands website and install Strands. So I'll click on Get Started, Python Quick Start. Remember that you can also use TypeScript, but in this case we'll be using Python. The first step is to create a Python project. First, I'll look at the folders I'm in. I'd like to get into the Documents folder. Can I increase this? Okay. documents. I have a folder here called Playground where I like to store all my play projects. And within that folder, I'll create a directory called furniture script. That's how I'll call mine. And I'll cd into that furniture script folder. And now I'll start installing the SDK. So I'll copy this. But it says Python command not found, so I don't have Python installed on my computer, my Mac. So I'll go ahead and download Python. Download Python 3.14.3. I'll click on that. I've gone ahead and installed Python. Right now, I'll create a virtual environment and install Strands within that Python virtual environment. So I'll go back to the Strands website and I'll copy this command. All right, paste that here. And then I'll activate source.venv /bin/activate. Now my virtual environment is ready. And what I'll do is I'll install pip install Strands agent. Strands has installed successfully. I'll go ahead and install Strands agent tools and the agent tools builder. Great. Now open up this file, this folder, furniture script, using anti-gravity. So I'll navigate to say open. I have it in the playground furniture script. And I have it there. What I'll do is I'll create a file called main.py, which will contain the code, and then I'll just create a file called prompt.markdown for the prompt I would use to generate this, to generate the code in main.py. Let me just increase the sizes of all this. Now what I want to do here is I want to drag and drop the folder that contained images. This folder, it's called baby children. I'll just drag and drop it in there. Add folder. And I think there's just a lot in there. I'll delete some. I'll navigate back to reveal in Finder. I'll navigate and I'll delete a lot of stuff. I don't want all of this. Move to trash. I need just a few. Yes. That's okay for that. And then here as well, I'll delete all of this. Let me see if I can deal with this. Yeah. Oh, there's a lot here. You can see kids rocks, baby linen. Take these out. All right, great. Yes, this is enough. Now what I want to do is I want to use a prompt to generate a script that will go through each of these images and create a corresponding metadata.json file. Within that JSON file, we'll have these details. So from the right hand side of the screen where your have to input the prompt. If you don't have it, you can hit, if you're on Mac, you can hit Command L and it will reveal the text box for you, or the text area. If I go to prompts, if you run this prompt, bear in mind that all these files, I'll save them to GitHub, and you would have them. You can just get it from GitHub. I'll have them on GitHub for you. So this prompt says, write a Python script using the Strands library to automate the generation of furniture metadata for an e-commerce catalog. The script should meet these specific requirements. AI setup: use the Bedrock model class with this model in a US East 1 at a temperature of 0.3. Tooling: define a tool called Save Product Metadata. Let me increase this as well. Yeah, okay. That accepts directory, file name, and metadata content. It should validate the JSON string and save it to the local file system. Agent logic: initialize a Strands agent with a system prompt for a luxury furniture catalog specialist. Strict schema: the agent must output a flattened JSON, no nested filter key. Required root fields. We have the product ID, name, image file, what's the DOM? You know this these agents. Anyway, I think I just had the agent just put in this the category, subcategory, and then the level if it's premium or whatever. Constraint: the total JSON size must remain under this for S3 vector compatibility. And then the workflow now: create a function called process furniture catalog that uses the os.work to traverse /catalog directory. So let's rename this to /catalog. Or to catalog rather, not slash. There's no, where is rename? Are you serious? Reveal in Finder. No problem. Catalog. And we drag and drop again. Just copy folder. Yes. All right, now we have the folder with our images. I still think there are a lot of images. What are these? I would like to delete this text files within the folders. Or I'll just let it be. If you go ahead and run this prompt in anti-gravity, you'll generate this main.python file. And within it is just what we had in the prompt. You know, this Bedrock model, which has Amazon novel. This Bedrock model, which has the model ID us.amazon.nova Pro version 1, which is Amazon's flagship generative AI model. And then we have a tool called Save Product Metadata. So this tool generates a product metadata JSON and saves that to the file system. And then we define our Strands agent and pass in the tool within this tools array and the Bedrock model. And then we'll give it the system prompt. Anyway, the agent gives it the system prompt because that's everything generated here was what we specified within the prompt.markdown file. And this prompt was actually generated by Gemini also. So I did not actually type this by hand. And now, since this our folder catalog contains folders within folders, we'll use those as categories and subcategories. So our agent traverses, or our script traverses through the folders right down to the image or to the images, and then generates the corresponding meta.json file. So for each image, we would have a corresponding metadata.json file. So if we navigate to terminal, if we navigate now to our terminal and run this main.py file, Python, okay, say missing dependencies. Using the login credential provider requires additional dependencies. You will need to install this before proceeding. Okay, so let's go ahead and do pip install. Okay, it has been installed. Let's try running it again. Your session has expired or credentials have changed. Please re-authenticate using AWS login. Exactly. So before you want to carry out this step, there's just one thing I want to make sure that you're aware of. Running the Bedrock model actually needs that you be authenticated and you have permissions to access this model. You have to be authenticated with your AWS account. So you can either use AWS configure or you use AWS SSO a single sign-on to login. Okay, let me go ahead with AWS login and see. I'm using root nodes. It's okay. I like using my root credentials. Okay, so with this, do I need to specify the profile here? If it doesn't work, I'll try specifying the profile and see. All right, so it's going through each image now and creating the metadata. If you can go back, quite a lot of images as well. All right, so if you can see, this is a JSON file for this image. Let's just go ahead and see what's inside. Look at that. So it has generated a product name and then the image file, which is the name of the image. This was what's dumb, I don't know, furniture, but I know about the category, the subcategory and the level. Anyways, we wouldn't be using line 5 and line 8. That's too much blind vibe coding for me. All right. All right. My script is done, and if I navigate back to the folder, I can see that for every image we have metadata, a .json file, and this is exactly what I need in order to proceed. From here on, the next step I want to take is to manually build my workflow. The reason why I want to do this manually is because I really want to test my workflow before I have it being created by infrastructure as code. So I will want to build this workflow with AWS Step Functions. I tried as much as possible to vibe code this section, but it kept on giving me so many errors, and I felt like me doing it manually would be a lot faster than trying to vibe code it. So the first step I did was I logged into my AWS console, and then I navigated to AWS S3. I created a bucket called Furniture App Bucket. And within this bucket, I dragged and dropped the catalog folder, which you can see here. And if I click on that, you would see this file called .gsstore. It starts for Mac folders. It shouldn't be here. Anyways, other folders here, you see the baby children, bathroom, Bedrock. It is Bedrock, bedroom. But take note of this, embeddings. We'll see why this folder appears here later. But just bear in mind, I dragged and dropped the catalog folder into this bucket. The next step, I navigated to AWS Step Functions. When I say navigated, all I did was I went up to the search bar and I searched for step functions. Yeah, just like that. And then I created a new step functions workflow or step functions machine. You click on this button to create a state machine. You can create a blank state machine. So you can give it any name. You can call it furniture workflow. And you'd have this blank canvas. Anyways, let's go back to what I created. I'm signed out. Let me see. If I go back to state machines, all right, so I created a state machine called Furniture App Workflow. Let me click on that. Then I'll go head over to edit so we can take a look at the state machine. I'll just close this a little bit. On the right hand side, we have a canvas where we can drag and drop actions, flows, or we have patterns as well. So the AWS team actually gives you some startup templates which you can use to accelerate your development. So if we look at the workflow on the right hand side of the screen, I'll close this as well. The first thing I want you to take note of is the map which encapsulates the entire workflow. As I mentioned earlier, we'll use a distributed map because remember we have a lot of items, a lot of folders within our catalog folder, and these folders have a lot of items within them. And these items will have to go through, each of these items will have to be processed by the state machine. And because there are a lot of items, to actually process them efficiently, we need a distributed map. So if looking at the configuration on the right hand side, if you scroll down, you'll see that I selected the distributed map here, which says high concurrency mode. Each map iteration is run as a separate child workflow execution. Supports large-scale S3 data sources. Exactly. And then for the item source, we're definitely coming from S3. Our items are in an S3 bucket. So I selected the Amazon S3 option. And then we'll move down for the bucket. This is the name of the bucket, Furniture App Bucket. And then it's within a folder called Catalog. So we add that as a prefix. Let me see if we have additional configuration. Nope. And then I set a concurrency limit to 10. The reason why I did this is because this can be pushed right up to 1,000. But the reason why I set it to 10 was because I told you about the fact that each item would have to be broken down into numerical vector embeddings using the Amazon Nova 2 multimodal model, embeddings model. And this model has a limit. It has a threshold on the amount of items it can actually create embeddings for at a time. So when I was actually building this application, I tried out so many different concurrency limit numbers here, and I just found 10 to be the sweet spot for it. So I went for 10. You can actually try out different numbers as well to see what works for you. But my limit was at 10. So I want 10 child workflow executions at a time. And then for the child workflow execution type, I chose standard instead of express. And there's a difference between a standard workflow and an express workflow. And for this case, my main reason for choosing standard was because of the execution time. I don't want it to be capped at 5 because for express, after 5 minutes, if the item hasn't been, if embeddings haven't been created with that item, then the workflow would actually stop executing. And I don't want that. So I chose the long-running standard workflow just to be on the safe side. And then I set a tolerant failure threshold as well. I said if 100 items fail, then the entire workflow should fail as well. And finally, for the results, I want the results to be exported back to my S3 bucket in a folder called results. Let me go back to S3 and show you. So here, so failure or success would actually be saved back here. And this actually helps me to really debug my workflow. So if the workflow fails, it will actually save the reasons why it failed. If you can click on one and open it up, you'll see that we have a succeeded_0.json file and a manifest.json file. So if it failed, you actually see a failed _0.json file, which you can open up and see the reasons why it failed. Let me see if we have some failed results here. All right, so we have failed here. If you can click on that, I'll just want to open this up. I'll download it. Yes. Open up. Can we? Jeez, how do I wrap this now? Anyways, an error occurred. No such key when calling the get object operation. Jeez, why can I not wrap this? I don't know how to wrap this. All right, it says an error occurred. No such key when calling the get object operation. The specified key does not exist. Exactly. I remember I went through this issue and I resolved it. But what I'm really just trying to say here is that this results folder will contain messages from your workflow, success or failure messages. So you just have to take a look at it. And then let's go back to our workflow, and we'll have the next step here, choice state. And the reason why I have a choice state here is, let's go back to S3, the S3 bucket. Inside the catalog folder, let's navigate to the baby, and then we'll see, wow, I had a lot of them. We'll see files within it. So we have JPEG files, we even have this stubborn file, and then we have .json file. And what we want to do is we want to create embeddings only for images, and the images, all images end with .jpeg. So we want that if it's a .json, then the workflow should not execute. It should not actually push it to the embedding stage. And that's exactly why we have this choice state. This choice state actually filters out all the .jpeg files and send them to the embedding stage. And that's what the condition here does. So we have a rule, and that rule says that any file that ends with .jpeg, this is it, rule number 1, send it to the next stage, which is the start async invoke step. And this is an asynchronous step that actually helps us to break down the image into numerical vector embeddings. So it's asynchronous. If we go to the configuration, we'll see that we have, for the arguments, we have this within it. It has the model, which is the Amazon Nova 2 multimodal embeddings model. And then the format is it's a JPEG format, standard image. The location where it has to pick the images from. We have this, which is static here, but once we have this workflow within our infrastructure as code, we'll swap out this, we'll make this bucket name dynamic, so it can work with it can work in any scenario where the bucket name is not furniture app bucket. And then where does it save the output? Where does it save the embeddings back to? It saves it back into the catalog embeddings folder. That's exactly why we have this embeddings folder here. And because this step is asynchronous, would have to actually wait for it, and then we constantly have to check on the progress report, on the fact that it has three states. It will be either in progress, the process would have either failed or completed. So we wait 20 seconds, and then we do a get async invoke. So this get async invoke actually gets the status of the start async invoke process. So we have another choice state here that has three conditions. The first condition is that if it's completed, then it should move to a Lambda function step, which I'll talk about this in a moment. The second step, or the second rule, is that if it failed, then it should actually just fail. Maybe in a real production app, you might want to do something else here. Maybe send an event, which will be ideal, or I don't know. And then the third, which is the default step, is that it's still in progress. So it should go back and wait. And after it waits, check, pull for the progress report, send it to the choice state, and then determine what progress or what stage the embedding is currently at. If it's in progress, go back to wait. If it has completed, move to the Lambda invoke step. If it has failed, then fail the step functions workflow. Now, once it's done, all our embeddings are inside the embeddings folder. Let me just show you. Let's open one up. Then we have this embedding image.json file. I'll open that up anyway with the text editor, no problem. And we see that here we have this embedding object, and it has an array of numerical vector embeddings. So these are the numerical vector embeddings for the image. And then it has a status as well. So this is really good. This is what we have to make sure that our Lambda function picks up and then saves this into a vector store. The next step I did was I went ahead and created a vector store. So I went back to S3, and if you look on the left hand side, you would have vector buckets. If I open that up, I have a lot of vector buckets. Sorry about that. But anyways, we have a furniture app vector bucket here, which I created, and then we have the furniture app index here. Into the properties. Now, while creating the furniture app index, take note of the dimension which I chose. So I needed the highest accuracy, so I picked up the 3072 dimension. I think multimodal AWS Nova 2 multimodal embeddings model supports 1024. Let me see. Yeah, 1024, 384, and 256. But I went with 3072, which provides the highest accuracy. And it's also costly as well, If you go back to our step machine or a state machine, I just want to show you something. If you navigate to the start async invoke step, you see here that I actually specified the embedding dimension here as well. So this has to correlate with the vector index you actually created. The dimensions of the vector index have to be equal to the dimensions here, to the embedding dimension here. Now we have a Lambda function here. I'll show you the content of it, which I vibe coded. It actually expects the S3 URI, which actually is the location of the embedding file. Let me show you. So if it just went through an image, if this was the embedding, and then it will pass it this location, and then it will pass it the key for the original image as well. It will pass it the key for the original image, which are called media file URI. The reason being that, remember that the .json file, the metadata.json file, let me go back. Bedroom. Okay, remember that it passes it the original key for the image. So let's say this is the original key for the image. It passes this in because this image name is the same as this .json file name. The reason is that we want to get this file because this file contains the metadata for this image. We'll use that metadata to actually save it alongside the vector embeddings for this image into the vector store, and then would still use this metadata to save it as an item into the DynamoDB table. So if I navigate back to the step functions workflow and I go to the Lambda function, let me navigate to the Lambda function. All right, so I see that here it has a configuration where it has a source bucket, vector index, and DynamoDB table. And then it gets both of the items within the payload. It actually saves the embeddings. It extracts the embeddings and saves them into the vector store using the put vectors method from the S3 vectors. And then it actually saves the item also into the DynamoDB table. Here, look at, we use PK and SK to represent the data in DynamoDB as a single table design. If you don't know about single table design yet, it's a design pattern where you save all the entities of your application into one single table instead of actually distributing them around as if you're working with a relational database model. So here we have the product, and then this is the UUID, which was inside the metadata.json file or the image metadata file. We save this as an item into DynamoDB table, and then we put the vectors alongside the metadata. See, into the vector store. And that's just about it. And this file was vibe coded. I'll share the prompt soon. But remember that we're doing this manually and we said we'd use infrastructure as code. So I'll go ahead and delete all of this and we will now navigate to anti-gravity and start building our application. In this section, we're going to look at two things, skills and MCP servers. That's all with respect to our Agentic IDE because we'll be using anti-gravity. I hope you've already downloaded and installed it because I already have mine running and I'm good to go. So looking at skills, it's an open standard for extending agent capabilities. A skill is a folder containing a skill.markdown file with instructions that the agent can follow when working on specific tasks. Now that this application is actually specific to our use case, obviously, we want visual search and we want voice chats, and they'll be using some specific models and some specific frameworks. We want to actually highlight all of those within our skills.md file so that when the agent is trying to solve the problem, when it's trying to write the code, it should always reach out to the skills.md file to grab more context and more information. So that's like providing the agent with more information and a lot of capabilities that it can use to accomplish our tasks. And then for the MCP servers, what we'll really focus on is AWS MCP servers. So we have a couple of those. I'll go ahead and open up my IDE and just show you. So if I go to on the right lane, if I go up to the top here, this additional options, this overflow button here, if I click on it, I'll see MCP servers, and then I'll click on MCP servers, and then I'll click on manage MCP servers. And here I can see all the custom MCP servers I have. And what I'll do here is click on view raw config. And now I have a couple of MCP servers which I have installed on my IDE, but here's what we should focus on. I'll close this. First is the infrastructure as code MCP server. So this actually helps my agent to write good and recommended CDK code for my application. It's very important. So I have this here, and I got this MCP server from the official AWS MCP server repo. So AWS MCP servers. If I search for that, I have the official MCP servers for AWS, this repo, and if I search for IC, okay, all of these are deprecated. AWS CDK development with security, compliance, and best practices. Use this instead. So if I click on that, what I have, if I scroll to the bottom, I think I would see the configuration. Yes, here's the configuration. And then we can see how you can query it. But that we'll leave that to our agent. But here's a configuration which you just have to copy and paste here. The next thing is building an application that is well architected, and I need an MCP server for that as well. An application that follows the well architected framework offered by AWS. And now, since our application is agentic, I definitely need the Bedrock Agent Core MCP server as well. Just giving our agent enough resources so it can carry out the its tasks perfectly. And now for billing as well, like I mentioned earlier, actually when I'm really when it comes to building, I love thinking about cost a lot. I want to build my application, deploy, and even use my application up to the point where it's now generating enough income, and I can actually keep running the application without burning too much money. Putting out there without burning too much money. So I always need to take note of the cost. I need to be frugal with the cost. The total cost of ownership should really be lower than what's actually being generated by the app. By the income that's actually being generated by the app should be higher than the total cost of ownership of the app in order for the app to live. And with this MCP server, I can make that happen. When I say make that happen, I can actually tell the agent to use this MCP server and, break down, give me the total cost of the app if it's being run by 10,000 users or by 2,000 users, just trying to make an estimate of if I'll be able to run the application in a profitable manner. If I can actually explain it properly. I have a serious problem with putting out my ideas, and that's actually one of the main reasons why I'm doing videos. I've started doing videos because I want to really learn how to put out my ideas to the understanding of another person. So here we have these 4 MCP servers which we'll be using for our application. And now for the skills, what I'll do is I already have the code and the prompts pushed to GitHub repo. So I'll go there and I'll copy the skills file and I'll create a new project and I'll show you how to add your skills, and then you get going. Back to the terminal, and I still have it inside the furniture script. What I'll do is I want to open up a new, I want to leave this and then I'll work here. So still in my playground directory. I don't know what directory you're currently in, but I'm in my playground directory. What I'll do is I'll create a directory. I'll create a new folder called furniture because I already have, do I already have furniture AI workflow? Anyway, I'll just call this furniture workflow. No, furniture app. And I'll seed into that. Well, I don't really know why I've even seeded into this, but I've created this folder. What I'll do is I'll open it up in anti-gravity. Open. Playground furniture app. And yes, now we have this. And the first thing I want to configure here is the skills.md file, which in order to configure it, I'll just go to Google anti-gravity skills. Look at the URL. And there are two ways you can configure it. You can configure it for global or for your specific workspace. And this is actually what I want, just this. So I'll go back, I'll create a folder called .agent. And if you see, this is it. Now within the .agent folder, we have another folder called skills. And within that folder, now we have the name. I would like to call this backend architecture or just architecture. So within the skills folder, we have, I'll call that architecture. And within the architecture folder, now we have the skills.markdown. See? Yes. So if I go to architecture and I would say skills. Is it skills or skill? Okay, skill.md. And that is it. You know, I think the first step is having, within the skill file, is having my font matter. But like I said, I already have this on GitHub. And what I'll do is I'll run to GitHub right now and copy what's already working, you know. So I'll go to GitHub. Where is furniture app? Okay. I'll share all of this will be in the description. All these links will be in the description. So you would have everything. And because I was saving the file to GitHub, I actually extracted the skills.md file and just put it here, like, you know, just pasted in it. What I'll do now is I want to copy that, edit this file. Need the raw one. Yes, that's what I need. Cancel changes and paste it here, and we'll go through it step by step. Now we have our beautiful skill.md file. Let's walk through it. So from line 1 up to line 4, we have the font matter, the name, furniture AI skill, the description, furniture AI visual search, and the voice chat, the Agentic platform, whatever. And then the context. This skill enables the replication of a sophisticated furniture AI platform. The architecture integrates visual multimodal search, that's using Nova multimodal embeddings, plus S3 vectors. Durable orchestration, AWS Lambda durable executions plus step functions, and a real-time bidirectional agent. Bedrock agent call plus Strands plus voice. Nova Sonic. Let's say Nova Sonic, which is the voice model offered by the bidirectional voice model offered by AWS. It supports automated product ingestion, high performance vector search, and a voice-enabled conversational assistant with Stripe payment capabilities. That's the context. Now for the architecture, I actually, this was also generated by AI. I guided it to generate this. Everything is generated now. Just have to guide it. So I separated it into 4 layers. We have layer 1, which is the storage and data layer. And it talks about the S3 catalog. So replicated as furniture catalog bucket stores raw and processed images. And then we'll have the S3 vector store, DynamoDB, and the key management service for encryption. Now for the second layer, we have the coordination and the API layer, where we use AWS AppSync GraphQL to build a GraphQL API. So we have a schema. In GraphQL schema, we search products, ingest products, invoke agent, and get agent WebSocket config for voice. And then we have the event bridge bus. So it routes visual search results from the durable lambdas back to AppSync via internal mutations. Like I mentioned earlier, if you've been watching, when a user searches for an image that finds similar images to like this chair, what happens is that when it starts the process of breaking it down into vector embeddings, it actually sends events, and those events are being brought back to the user for the user to know at what step the search is. It's really great for real-time feedback. It's also great when you're building chat applications, real-time conversations. And then we have the AWS step functions. Furniture ingestion workflow orchestrates the parallel processing. We've already done this part. What we'll do is that we'll just copy the JSON for that workflow, which I explained, and we put it here, and we're good to go. Now the third layer is a compute layer, the Lambda logic, where we have the ingestion engine, which is called process images, or they should call it process images.py, and it converts images to vector embeddings and saves them into the S3 vectors. We looked at that when we're looking at the workflow. We saw the Lambda functions within the workflow that actually grabs the metadata and the vector embeddings. It saves the metadata alongside the vector embeddings within AWS S3 bucket, vector bucket, and then it saves the DynamoDB item, which is also made up of the metadata of that image, into DynamoDB. So it does both of those. And it's and then we'll have the durable visual search. The durable Lambda handles long-running multimodal embedding requests and vector queries. And then we have the agent runtime, which is the agent runtime.py, a fast API-based Bedrock agent call app using Strands. Supports WebSocket-based bidirectional voice with Novasonic and RESTful agent invocation. Then we'll have the agent tools, agent core tools, MCP compatible tools for search, product info, and mocking orders. Then we have now the fourth aspect, which is agent core plus the MCP integrations, where the gateway actually has, it takes the Stripe MCP gateway and the Bedrock agent core gateway. Those are the two gateways we'll have. But here, in this gateway, we had to have these tools as well, because that's what we're adding to the gateway. Tools are added. This Lambda tools, this agent core tools, is a Lambda function, and the gateway actually supports 4 targets: Lambdas, MCPs, OpenAPI, and SMITI APIs. Technical constraints and standards. Tooling: AWS CDK TypeScript in Python 3.13 for Lambdas. We have the CDK S3 vectors, dependencies, strands. Okay. Ensure text model ID, Novalight, and voice model ID, Novasonic, are correctly set. Ensure that. Well, this was when I was, facing a lot of issues, and then, I just had to let the agent note it down so that when you run this MD file along within your Agentic IDE, you should read up all of those, and it shouldn't make the same mistakes I made. And a step-by-step implementation guide for anti-gravity. Project initialization: initialize a new CDK. Yes, infrastructure provisioning, build with S3 buckets, DynamoDB, index, you should not forget this. The Lambda logic, create all of this. Agent core setup, creates this. Workflow deployment, deploys that, would have to bring it in. Point the Flutter or React application to. We'll get to that later. But we'll save this. The next step is, let's look at the prompt file. The prompt file is where you would execute each and every prompt in order to rebuild this application. But there's one thing I want you to bear in mind. Agents are non-deterministic. You can I mean, if you've been working with agents by now, you should know that the same prompts that will be generated by my agent, give it to your own agent, it will not generate it exactly the same way. But I'm glad that I have the code here, which you can use as context for your agents to see what a working application looks like. And then you should either copy that or improve upon it. I don't know. But I just wanted to put that out there. The next step is we'll look at the prompts.md file to see each prompt, how you'd execute each prompt or what each prompt actually means. Now I have my skills set. Bear in mind that I still have my MCP servers. Manage MCP servers and yeah. So I have them here. Let's move to the repo and look at the prompts. So I'll navigate back to the repo and click on prompts.md. And here we have all the prompts which you have to run to recreate this project. The reason why I don't want to run them again is because lately Anti-Gravity got stingy with their credits. Let me show you something. So if in Anti-Gravity, if I go to the settings and I go to the models, you see here that I don't know what happened, but their Gemini 3.1 Pro, they've greatly limited the quarter, reduced the model quarter, and it refreshes every 6 days. No, I'm still waiting. Sometimes it refreshes, and before you want to use it, it says no, it needs another 6 days. It needs 6 more days to refresh. So now I'm just left with Gemini 3 Flash, which is good, but it also depletes really, really fast. But it refreshes every 3 hours. Oh, 4 hours. No, 5, I think 5 hours, something like that. But what I'm just trying to say here is I cannot go ahead and recreate this project by running these prompts because I'll run out of tokens before I even get to the second one. And I don't want to do that again. I have lots of other projects to run. I'm selfish. But I know you have a lot of tokens. I don't know what you're using. If you're not using Anti-Gravity, you'll definitely be using something like maybe Cloud Code or Codex, which I think those guys have generous model quarters, and you can easily run the project. Or you can re-implement the project a lot faster. Your agent, but not you. So let's go ahead and read through it. Rebuilding the Furniture AI application, a guide for agents and students. All right. This document provides the structural blueprint and sequential prompts required to create the Furniture AI app. This application features a React front-end, a CDK-based serverless back-end, and an advanced Bedrock integration, including durable lambdas and vector search. Great. For this front end, we'll look at it. This will be the last part that we'll get to look at. You would enjoy it. And then we have the infrastructure, which is AWS CDK with TypeScript. You can also have it with Python. You can have it with what else? Ruby, I think so. Java as well. Then for the API, we use a GraphQL API, IAM, the API key, and the Cognito authentication. The search and the AI, we have Bedrock, Nova embeddings, S3 vectors, durable lambdas, storage, S3, orchestration, AWS step functions, event bridge, and overnight. Sequential rebuilding prompts. So the first phase one is the storage and identity foundation, where you instruct your agent to initialize an AWS CDK stack in TypeScript. So what you do is you copy this, and then you come back to, you see this project, just open up the prompt and you start there. Just like that. And it starts. After that, after it completes, you go to the next, the API scheme, the AppSync API and schema. After that, you go to the visual or the durable vision search backend. After that, you go to the Bedrock agent core and gateway. Remember that you have the repo here, so if your agent is kind of stuck or if something is not working, you can always provide this repository or files within this repository as context. so your agent can actually use them, because this is working code. We'll test it out. This is working code, and you can provide it as context for your agent to unblock itself or to do it the right way. And then at the app, we have the critical gotchas and troubleshooting. So this is the easy part, letting the agent work on it. But at the same time, we have to understand what the code does. If the code is actually, or if the agent actually wrote the code the way it has to be written. Bear in mind also that I'm not a beginner. I have a little bit of understanding of the fundamentals. So I know how the configuration should be. I know how a CDK resource should be configured. I know where, to go and grab CDK resources. Even though I've provided an MCP server to my agent, which it can actually get the recommended CDK code to implement certain tasks, I also know where to go grab other CDK resources and use. So what you should do here is clone this repository. So let's see. Git clone. The purpose for cloning this repository is just to use it as a reference, for your agent. We're getting past that stage where you'd have to be reading code a lot. Like we're getting to a point where you'd have to create another agent to read and confirm that the code actually works the way it should work. Back in maybe a couple of months back, I think last year, the way we should have been doing it is that type along stuff like, okay, within the CDK file, type public static void main. We're not doing that any longer. This is 2026 and it's my favorite year, the year of agents, and we'll just, give the agents some work to do while we're doing some other work. Great. So I've cloned the repository. I'll go ahead and unzip it. Where is that? Go to playground. Okay. Now I have it here. I just want us to walk through the code, check it out, see some stuff, just explain some stuff around, just trying to understand the entire project structure. And you can use it as context to rebuild the project, while learning a thing or two with your agent. The first step is the workflow. And let me show you how I got this workflow here. If I go back to my AWS console, state machine. Back to my state machine, if you look above, we'll see design code and configuration. I'll switch to the code tab and I'll copy this JSON. So I'll copy it and go back to anti-gravity, and this is exactly what we have. And I just want to show you something else. You see we have the bucket name here as a dynamic value. We'll do this value substitution from the CDK infrastructure. We did the same thing for the Lambda function. Lambda function here. So this is good. You don't have hard-coded function names or S3 bucket names or any resource names within it. So this file can actually be dynamically used within other CDK projects. Now let's go to our CDK stack, which is here. And I just need to run npm install, and it will install all the dependencies within my package.json file here. but I don't want to run that. But we see that it defines an encryption key, and then it has a catalog bucket, and the bucket is called Furniture App Catalog version 2. We already have version 1. It gives it allowed methods, and then it creates an S3 vector bucket as well with a vector index and a DynamoDB product table. It creates an event bridge bus. It creates a Cognito user pool and a Cognito user pool client, which we'll use for authenticating into our API. And then the secrets manager, where we'll save the Stripe secret key, which the application will actually use, the agent will actually use to create Stripe payment links. And now for the GraphQL API, we have the default authorization, which is an API key, and then additional authorization modes, which we have the IAM and the user pool. The IAM here is because we will want services to speak to each other. What I'm talking about here is Event Bridge will talk to AppSync. You can subscribe for real-time events, and that will actually be authorized by the identity and access management token, So we have to give that authorization type. I'll also show you how we can use, or how we use AppSync directives to enable this. But this is used to make sure that AppSync and Event Bridge have the permissions to access each other. And this is for the sign in to onto our platform, user permissions. And then for the log level, great. And if you want to know more about creating AppSync APIs from scratch, the Cloud Academy can help. It has a lot of AppSync stuff. We have IAM rules for lots and lots of IAM rules. Yep, identity pool. Remember, we'll have a front end, so we'll need this on the front end for authenticated and non-authenticated users. Then, so all these permissions here for the front end as well. Our Amplify app will actually save images to public visuals, and our application needs permissions to access this. For Lambda functions, we have on the first one is the get upload URL Lambda function. Now this returns a pre-signed S3 URL, which we'll use to actually push data into S3. When a user submits an image, we use a pre-signed S3 URL to actually push images into the S3 bucket. And that's why we gave it this permission on line 2, 3, 4. Should I increase the sizes? Where am I? And then we have the next Lambda function, which is the get pre-signed URL Lambda. This should be get download pre-signed URL Lambda. When we actually find images, vector data inside of the vector bucket, and we return it, and we return the images, we need to generate pre-signed URLs for each of those images, which we will now use on the front end to display the image. And so the user can see them. We would actually see how we do that in the demo. And then we give it read permissions to the catalog bucket. And then for line 260, we have the catalog trigger Lambda. This actually triggers the catalog ingestion step functions workflow. And then we have the visual search trigger Lambda. This actually triggers the Lambda durable function for visual searching. As well, if we scroll down, we have on line 316 the batch get item Lambda function. When we get similar images from the vector store, and we there are always many of them, there are about 5 of them, we want to actually get the items for each of those images, and the most efficient way to get those items from the DynamoDB is to get into the images, get the metadata, the product user unique identifier, and then we do a batch get to get all the items from DynamoDB at once. This is exactly what this Lambda function does. And you see we grant read permissions to the product table. Then for the visual search workflow, yes. If we see on line 347, we have an execution duration, an execution timeout of 365 days. That's the Lambda function can run for 365 days, but this is a visual search function. Would the user wait for 365 days? No. And here on line 344, we have a timeout of 5 minutes. So I don't know which one the system will pick here, but I'll have to change this to make it like it has to be real. This has to be minutes, not 10 minutes. It should be a maximum of 2 minutes. All right, 5 minutes. And then keep that function around for 7 days before the execution around for 7 days before you delete it. Is that so? Yeah, so you can use that for auditing, but I think you can increase this as well. But also think when you keep the function around with the logs and all that, they are costly, so you pay for that. They provide the right permissions to the durable function, this checkpoint durable executions, get durable execution. If you want to know more about Lambda durable functions, if you go to EduCloud Academy and just search for durable, you'd see introduction to Lambda durable functions, and you'll see why we give all these permissions. Environment. Okay, process images Lambda, and here we already saw this when we were looking at the workflow, where this Lambda function actually saves into the vector embeddings into the vector store, and then items into DynamoDB. And we actually give it the right permissions as well. And then for the state machine, this is the definition substitution, the bucket name and the function ARN. If we go back, this is the function ARN. You see how we define it here. This is how we substitute that. Same with the bucket name. And then the path for the function workflow, furniture app workflow.asl, Amazon States language.json. That's the same way we have it there. What else do we have? Okay, now we have AppSync and Event Bridge. We define a role, and we actually make sure that one of the targets of this role is the mutation. We'll look at this mutation when we're looking at the GraphQL schema. So this mutation, when you subscribe to this mutation, you get back real-time events. And now we have the visual search queue. Like I said, there's a queue between the S3 bucket and a Lambda function. So that queue actually makes sure that it will handle errors gracefully, and it also makes sure that our Lambda function processes requests without throttling. Makes our application fault tolerant. And now we have Lambda data sources for AppSync. If you notice, we have ourselves a dead letter queue called the Visual Search DLQ, and it's attached to our queue. So this DLQ actually saves 40 messages, and it has a retention period of 14 days. So save these images and have them redriven by the developer of the system or the admin. And if they are not redriven within this retention period, dispose of the messages, so the messages will be lost for good. This is actually a good practice. If you create a queue, an SQS queue without a DLQ, then the messages that cannot be processed by the consumers of this queue will be lost forever. So if once you have this DL queue attached to your queue, then the messages that cannot be processed by the consumers of this queue will be saved here for 14 days before finally leaving the system for good. Now our queue has a visibility timeout and a maximum receive count. The reason for having a visibility timeout here is that when a consumer receives a message from the queue, what it does is that it hides that message. The queue now hides that message from other consumers, and it gives the queue gives the consumer this timeout to process the image, to process the message. And if it cannot process the message within that timeout, it makes the message visible for other consumers to pick it up. Now, if another consumer picks it up, let me say Lambda B picks it up and tries again, and it cannot process the image, it cannot process the message within that visibility timeout, then it sends it back, it makes it visible, and another Lambda function like Lambda C picks up the message as well and tries. If this happens 3 times and none of the Lambda functions or none of the consumers can process the message, then the queue actually sends that message to the DL queue. Now, the reason why we have 300 seconds for our visibility timeout, which is a lot higher than the Lambda timeout, is that we don't want 2 Lambda functions processing the same message, especially in systems like payment systems, ordering systems, and systems that are not built to deal with duplicate processing. Normally, you don't have to have two Lambda functions or 2 compute instances processing the same message or running the same processes, unless that's the use case of your system. But for this case, that's not what we want. We want a Lambda function to process one message, and if it's unable to process it, it leaves that message and lets another Lambda function take over. Then if we scroll down, this is where you see that when an image gets uploaded to the catalog bucket inside the visuals folder or directory, or the public visuals folder directory, because this will be used on the front end, or this is used by our front end, then the visual search queue should kick off. Now, if we take a look at our SQS event source, we have a batch size set to 10 and a maximum concurrency set to 5. So what this batch size here actually means is that when your Lambda pulls SQS for messages, it will try to grab 10 messages at once. This is really good in terms of cost effectiveness, because we don't want that each message to spin up a different Lambda function, because if this is not set, then 10 messages will spin up 10 Lambda functions, which that's not cost effective. And then for a maximum concurrency of 5, what we're actually saying here is that we want to limit the number of Lambda instances that can read from this specific queue at a time to 5. Remember, as said, we have the Amazon Nova 2 multimodal embeddings model, which has a threshold. It has a limit to the amount of images it can process at a time. So with this maximum concurrency set here, we want to make sure that we're within the limit of that model, so that our Lambda function doesn't throttle. And if we go back to the Lambda function that triggers our visual search workflow, this Lambda function is this is what gets messages from the SQS queue. We see that it does that in the for loop. Now we have on line 6, 7, 8, we have the Agent Core Tools Lambda function, which has functionality for our e-commerce products, get product, add product, create order, and all that. We'll actually look at it. It's inside the Agent Core Tools.py file. And then we have the AppSync agent resolver Lambda function. And I think this is actually what calls the agent core endpoint. So we'll submit the endpoint alongside the prompt and we get something back. I think that's it for the AWS CDK resources. I've just quickly, skimmed through it. You can take your time and really go through it to see how everything works. And if there's something you don't understand, you can just prompt the agent and it'll definitely explain that to you. If we navigate to the Lambda folder and we I would like to look at the agent core tools because that's the most interesting part of the application, where we have we define tools to get all our stuff, and these tools will be used we'll attach it as a target to the agent core gateway. So if you see here, we use a delimiter to see how we define the tools. This is actually how to define the tools. And I've realized that the agent couldn't really, build this, code this properly. And what I did was I searched for agent core. Yes. AWS has a good repository. Yes, agent core samples. Here, tutorials. And you'll see if I click on gateway, we'll see Lambda into transform Lambda into. We have target Lambda. And it has all the code. You can actually download this repository. You can clone it and you run all of this code to understand how to build a myriad of projects using Agent Core. What I did was cancel. I took the URL here and submitted it as context to my agent, and it created this file properly. So we have a tool name called Get All Products, and if you can look at Get All Products, what it simply does is it scans our DynamoDB table and returns 5 items. And if I can talk about this here, we don't want to return all the items. What I realize is that on the front end, when I asked my agent to fetch all products in our database, what happened was it was trying to get everything and just bring back in a non-paginated manner. And that broke my front end, and it broke the agent because the agent kept on running out of tokens. And I couldn't quite wrap my head around why that was happening. But now when I specified that I should bring back only 5 items, and then it was working perfectly. So here, the right way to do it is to actually paginate through the content, through the products. But for this use case, I just said you should bring back all the products, but now limit it to 5, so that it doesn't break, my model doesn't run out of tokens, and my application functions properly. Get products by category, same thing. And then we can create an order. It creates an order. But here we don't have the tool to generate a Stripe payment link. We'll see how that's done later on. If you can just look at other Lambda functions, get item Lambda, there's not really nothing surprising about it. This catalog trigger Lambda function just triggers a state machine. Now we'll create a Stripe MCP server, which would act as a tool-enabled bridge between the AI agent and the Stripe financial system. Now we've defined tools to actually create checkout sessions and to create the payment link, which our agent would need in order to create the payment link and return it back to the user. And this is also a good secure way to access Stripe, because see, from line 12 right up to line 19, we actually get the Stripe secret, which we saved in the secrets manager. So it's actually a perfect way to access Stripe. And then after we create our MCP server, we deploy that to the agent core. And we'll actually see how we'd use that within the agent. Before moving over to the agent, let's move to the next Lambda function, which is the function that triggers the visual search workflow. Remember, it gets its data from the SQS servers here, and then it invokes the Lambda durable function, which is the visual search workflow. If you can look at that, let's scroll down to, all right. So here's the Lambda handler on line 166. And what happens here is that it has steps. So the first step, it gets the image and then it generates embeddings. So it runs the generate embedding step. If we can move there, we'll see that here we have functionality to generate the embedding. And it still runs the start async invoke method, which is asynchronous. Remember, we actually accessed this method, but using direct services within the AWS state machine. Here now we are actually invoking it using the Lambda function. And then it returns a response. So if we go back again to our Lambda function, so it generates the embedding and then it checks for the status, if it's actually in progress, if it's completed, or if it failed. So we get the status. Let's just navigate to that. So if it's completed, we'll actually get the embeddings data and return it on line 106. Once we get the embedding, we can now use that to search the vectors. So we move to the vector step, and here we do a query vectors. So we pass in the bucket name, the index name, and the query vector, which is the embeddings. And we return the results. And then we'll also check if the metadata within those results have a product UUID. Let's move back down. And then for the next step, we have to fetch the details. What happens here is that we extract the product UUID and then we do a batch get item search. So invoke the Lambda function that does the batch get item from DynamoDB. And they'll also return the result. And then finally, we push those results back to the front end using Event Bridge. So here we put events within Event Bridge, and every client that is subscribed to the mutation that is a target of this event or this Event Bridge rule would actually receive the updates. That's actually how the visual search works. Step 1, 2, 3, 4, and 5. Now let's take a look at the agent folder and see what's within it. The first, from bottom to top, we have the tool schema. So this tool schema is actually generated based on the Lambda target. What's the Lambda target? The Lambda target was the agent core tools. So each of these tools here has a schema. For the get products by category, we see that we require the category. And if you go to the tool schema and look for get products by category, here we'll see that it has a properties category, a type string, description, and then it requires that category. The next file is the setup agent core gateway, where we attach both our targets, the Lambda AWS Lambda function, and the Stripe MCP server, which we created using the Stripe proxy here. And finally, we configure the gateway. And then here we have the agent runtime, which is mainly just made up of the bidirectional voice model. So we have two models here. Let me just show you. We have the Amazon Nova 2 Sonic model. And then this is actually for audio, for voice. And then we have the Anthropic Claude 3 Heiko. And really, I don't want to use this model here. So I'll go ahead and change it. Model catalog. The Nova 2 Lite. I would like to use this one. Copy that. And then I'll replace it. Yes. So we have two agents. We have the agent for text and we have the agent for voice. See, there's a lot of it. This is what they call AI slop code. Right, but it works. And I think with time we'll have to build another agent to really stress test this code generated by another agent, you know. I think that's it. The next step is I would like to show you how to how we deploy it. Even though it's still the agent that deployed this, all I did simply was to just test the app. Right now, go ahead and deploy the app. As you can see, I'm already within the Furniture app GitHub folder. The first step is I would want to install all the dependencies. So next step, I'll do CDK sync. In a real application, this should be done using GitHub Actions, using a CI/CD pipeline. So we successfully synthesized the CDK app, and let's do a CDK bootstrap. I think I need to sign in again. Once you've successfully deployed your application, you can move over to your AWS console, and at the search bar, you can search for Agent Core. Click on that. On the left-hand side menu, just click on Runtime, and you would see your agent. So here I call the agent Furniture Agent. If I click on that, I can see how to invoke the agent. And if you see, if I scroll to the bottom, it has versions 69. So I've deployed this application, this agent 69 times. So every deployment creates a new version. We'll come down and look at the invocations later on, but what I want you to pay attention to is the gateway. So if we move over to the left-hand side menu, we can see gateways. Click on Furniture Gateway, and you can also see how to invoke this gateway. With a Python SDK, with raw Python, with Strands as an MCP client. Then you can see the two targets we attached, the Furniture Lambda target and the Stripe MCP target. And there's a lot of stuff. We spoke about the fact that we had to give our agent memory so it doesn't actually forget our conversation, but we haven't done that yet, and I think that will be left as a task for you to complete. What else? I'd like to see observability. Okay, no invocations. I need some invocations.